And now you can start.
Okay, got it. Okay, so again, my name's Lee. I'm doing the image classification problem where we're trying to accurately identify whether or not a chest X-ray contains pneumonia in the image. So just a brief overview, we're going to be looking at methods, libraries, a little bit of background on what pneumonia is, the business question. I'm going to show you my multi-layer perceptron, show you what I have for my convolutional networks, and maybe some like ideas about how we can implement this technology into future areas of medicine. So the methods, we obtained our data from Kaggle. We had 5,000 images from our training subset, 624 from our testing, and 16 from our validation subset, which were really we didn't use in this presentation. I used a whole mess of libraries for mine, all just used for various reasons. I talked to Ben Jacobson, our technical instructor, a lot. I consulted with Sam a lot, future MBA right there, and I got therapy sessions from our instructor, Yish. So what is pneumonia? Pneumonia basically is an infection of one or both of your lungs. It's caused by microbes that infect your airways. It's mostly serious in people who are immunocompromised, older, children, and people who often partake in, inhalants. Treatments are varied based on the severity of the infection. If left untreated, you can go into septic shock or respiratory distress and end up dying. So the easiest ways to detect pneumonia are going to be probably X-rays. You can also go for other various methods by, referring to your provider. So our business question is, using past X-ray images, can we construct a neural network to accurately predict pneumonia? And I have just some examples of pneumonia here, where some lungs here, where on the left you see a normal, a healthy patient's lungs, and then in the middle and on the right side you see some cloudiness represented by the inflammation that is caused by the bacteria and viruses in your lungs. So my first example is going to be a multi-layer perceptron. Here I have just a very, very basic multi-layer perceptron. We use this just to establish kind of a baseline model, because multi-layer perceptrons are they give us a general solution to our complex answers. It's not very, very specific in the sense where we can customize it to the point where like we can get exactly what we want. That's how I picture a multi-layer perceptron. You're kind of getting a general answer for a complex situation where you might not get the best answer possible. So here, running it with 200 epochs and with a batch size of 100, I was able to get a 77% accuracy rate. If I did add a dropout rate before it crashed, I was able to get the percentage up to 81%. And I did have a confusion matrix that ended up not being able to run again to accurately show that. So my next one is on my basic convolutional network. We use convolutional networks, like I said, it's able to handle more, and we're able to customize them more because of our convolutional layers. And then because we're using a kind of like a binary output problem where either a patient has pneumonia or no pneumonia, is able to give us a sigmoid, able to give us a one output that says, yes, this person has pneumonia, or no, this person has pneumonia. So running with these parameters for my baseline convolutional network, I was able to get an accuracy rate of 70%. Again, this is adding no parameters, no like early stopping, no nothing like that, giving us accuracy rate of 70%. And that shows there's a lot of overfitting here. It's not really accurate. So for my next one, like I told you guys, I tuned with Talos, and it was able to give me some of these parameters that I tried to input in. This code took me 10 hours to run the first time, so it was a very lovely process. So by inputting these those parameters that you saw on the last screen into this, I was able to increase on average a little bit higher, get a little bit higher of a percentage and accuracy rate. Wasn't able to run the evaluation code on that. But again, the numbers are a lot higher than what they were before. And I'm also running another CNN model right now with early stopping and a different learning rate. And I'm getting about 75% accuracy rate right now. So again, thank you, Talos, for showing me better ways, and thank you, Sam, again, for telling me what I needed to do. So again, I couldn't evaluate using my Talos model, but based on what this model is showing, is if I did run this model, I would be able to get a 97% accuracy rate, which is what we're kind of looking for, right? In the terms of healthcare, when you're talking about a serious disease, you want a very high accuracy rate. You don't want oh, if this might be pneumonia, this might not be pneumonia. We're just going to send you home, and then you end up dying at home. So results in future work, again, we were like, this is very loose. We were able to accurately predict pneumonia on images. Again, I don't have, I wasn't able to run everything. In the future, I will. Again, future work with what I mean by that is like next week, I will be finishing up the project over in Jupyter Notebook, using various other methods like early stopping, changing the learning rate, editing my batch sizes, editing my number of epochs, and then including confusion matrices and stuff like that to better solidify and take that point home. And then for future work, I believe that honestly, medicine and technology are going to combine together more and more in the future. Right now, I have a friend that's a urology resident. He's actually using robots to help, perform more precision-based surgeries on people. So and we can transfer that to here, right? We can probably in the future use the technology to either, help detect like bone fractures in orthopedic patients, or even like cancer in, other areas, in like, breast cancer, testicular cancer, GI cancer, stuff like that. So we're able to translate this, take this technology and move it to other parts of medicine. And I look forward to, hopefully be part of that when the time comes. And that's all I got for you guys.
Great, thanks, Lee. All right, let's move on to Nelson. That's the order that we agreed on, right?
Yeah.
Yes. All right, 1 second. There we go. And there you go. Everything look all right? Okay. Hi, so my name is Nelson Hanau, and my project is on stock price forecasting. So as an overview, I'm using time series forecasting to predict stock price growth over a default number. I picked 60 days. I figured 2 months would be a good time to kind of see if a stock would grow in price or not. In this presentation, I'll be performing an in-depth analysis on Mongodb using a bunch of custom-built pre-processing and modeling functions that I created. Mongodb, I'm using it mainly because this one has been a thorn on my side. I really wanted to invest in it a long time ago, right before it boomed up, and I'm still angry at myself for not doing so. So that's why I picked this one. And overall, once I do the in-depth analysis on MongoDB, I'll kind of just like show it off on other stocks that I kind of handpicked depending on the industry. And I'll be rating these models based on the lowest RMSE for now. So my data comes from Yahoo Finance. I basically download everything from the historical data on there. And the 5 stocks that I'm going to be working on are American Airlines, Amazon, General Electric, Intel, and Tesla. So it's like a decent little mix of stuff here. And I'll be looking at the last 5 years of data just because the further you go back, it's not really useful anyways. Okay, so here's my EDA for the MongoDB stock. So here on the left, you kind of see the overall trend as of 2018 actually. And this is what it's looking like. I was hoping to kind of get it here, in this point before it boomed up and then continued to go up. And I think it actually almost doubled in price back in 2019 as well. One of the functions that I created just returns the best number of periods difference the data for, and just using the Dickey-Fuller test to provide a significant value of the number of differencing, or rather to measure the removal of trends in the data. And from here, we use this difference data to get the p-value, which you get from analyzing the partial or the PACF graph here. And this tells you how many lags of autoregressiveness you have to take into account, or rather how many significant lags of autoregressiveness you need to take into account in the model itself. And on the right, we have the Q value, here we go, that measures the significant the lags related to the moving averages. Now here's our models here. I use 3 models in general. One is the ARIMA, the next one is the AutoARIMA, and then the last one was the Facebook Profit. However, ARIMA and AutoARIMA are very similar, so I kind of just showcased these two for results. As you can see, the base ARIMA model here kind of underpredicted the data quite a bit. It followed the trend from like this period of time over here. And the RMSE I got here was $92.11. Using Facebook Profit, it was actually a much better fit. As you see, it kind of went right in the middle of the test data, and I got an RMSE of 65.79. However, I also introduced certain transformations on the data. So in particular, the log transformation, which helped improve some models or the performance of some models and kind of decrease the performance of others. So in this case, the logged ARIMA based model performed much better than the other 3, including this one on the right, with a RMSE of $58.08. And as you can see, it kind of goes right through the middle of the data right here, nice and clean. Whereas the Facebook Profit model on the log data performed pretty terribly. So it overpredicted the prices here with an RMSE of almost $269. So it's pretty bad. Next up. So overall, the best model for MongoDB here was the ARIMA. So that's what I used to fit the entire data that I had and forecast the next 60 days. And I added these arrows here to kind of show the trends and how they affected the forecasting here. So this period here after April 2021 contributed more to the forecasting of the next 60 days than this period over here. And I am predicting or forecasting a 17.41% growth rate in 60 days. So if you want to invest, get it now. So you can make the most. All right. Some additional results. So after running that same process on a bunch of the other stocks that I had here, just some examples. American Airlines. We have here a predicted growth of about 1.68. And given the nature of the airline industry during these COVID times, we can kind of it basically makes sense to it. It's like, we're still really unsure on where this industry is going to go. Whereas Tesla, it has been growing quite a bit over the past 2 years or so. As you can see here, it actually started in less than like $50 in 2019, and it's skyrocketed to almost $1,200. And this model basically predicts that Tesla is going to end up with a 17.01% growth rate in the next 60 days, unless Elon Musk decides to tweet some controversial things again, which, as you can see here, this is actually the results of some of that. Now, this table kind of shows the RMSEs across every model that I ran for these stocks. And it also points out the best model, the best RMSE associated to that model, and the expected 60-day growth percentage for that stock in particular. And one thing I wanted to point out is Facebook Profit doesn't really appear here at all. But if you look a little closer, it usually came out second place or close third place in many instances. So I believe that the the tuning of the parameters for the Facebook Profit could have used a little bit more work if I had more time to play with it. And this is just a visualization kind of showing the growths in comparison to the others. So General Electric is expected to do not too bad, but not as good as Tesla here, which is kind of like the main winner around here. So for conclusions, MongoDB and Tesla have the highest rates at over 17% in the next 60 days. So if you want to look to invest, I might consider taking a peek at these. However, I do advise some caution just because, hold on, oops. Yeah, as you can see with the light blue here, there is a lot of uncertainty, in my opinion, when it comes to these things, because I use a confidence interval of 0.1. So, but with stocks in general, we kind of know it's pretty hard to predict. Otherwise, everybody would be making a ton of money, right? So some next steps is I would like to train a neural network on stock data just to improve forecasting accuracy and see if like there's any kind of meaningful insights you can gain from that. And some additional variables I'd like to introduce is stock sentiment analysis, company financials, and just, I guess, overall news data and things like that from the web to see if any of that stuff also affects. Actually, we know it does affect the price of the stocks, but actually having hard data to support it. And then finally, automating the process overall. So just getting many stocks, running the best models on it, and see if any kind of patterns or trends stand out and make some money. All right, thank you. That's my project.
Awesome. Thanks, Nelson. All right, next up, Amir. I realize this order does it really nicely, so there's no two like neural network projects in a row. Good job, everybody.
Okay. Okay, can you guys see my screen?
Not yet.
Let's try it again.
Oh, yep.
Okie dokie. All right, so yes, welcome to Amir's very hodgepodge put together neural network analysis, and it's going to be the difference between American cartoons and Japanese anime, or you call animu, or any offensive term, otaku, TV that you want to use. Well, it's going to be by Amir daily and subsequent people that may need it in the future. This is for all the companies that need to automate content definitions in terms of like labeling, I guess, anime or cartoon categories, and then to all the people that confusingly watch me on the train as I'm laughing to some random show. So yes, why does it matter? It really doesn't matter. But you can create a better experience for people who frequent this content, and like create a more streamlined process for like labeling content instead of doing it by hand when you're adding it to like a streaming service like Hulu or Netflix. Hopefully, this can be like a first step in expanding it to different categorizations of anime and American animation. For example, like for like Japanese animation, you have like shonen, shoujo, just say, and like etc. The kind of definitions on the bottom, I'm not going to go over that because it's probably just too in depth and people really probably don't care. But you have targeted audiences, whether they be like young boys, older men, young women, older women. Some shows that people may like Naruto is like shonen, which is geared towards young boys. And then you have things like, I'm not going to say that one because it's for girls and it's not appropriate. But anyway, moving on. So for Company X, we would like to give like custom driven content for like a streaming service, and hopefully what my goal is in the future is to, instead of have a program that is it is a recommendation system, honestly, when you think about it, but like not something that's recommending me shows that people want, like people frequently watch, but what they like in terms of content. So I noticed that when I watch Hulu or Netflix, I noticed they're changing it recently to get it more like customized, but traditionally what I'm used to is that, oh, I watched Dragon Ball Z, so then they show me every anime within like some odd fighting category, and most of it I probably just don't even like, I'll probably never watch, and it's not really customized to like the type of anime that I particularly like, which can get nitty gritty in terms of like the content and what's being shown to me, because there's so many different types of actiony anime. That will be for future analysis. This is just trying to do the first step of finding out what is the difference between a cartoon and anime and see if we can create like a discernible difference. Yes, and this will be really important for, okay, whatever. Actually, I'm just gonna skip the last part. Okay, so what is the difference between anime and cartoons? The biggest thing, I just put this up here just for reference. It's easy to break down. I will say for me, I would definitely say it's definitely facial structure and how their bodies are built. This is saying that their eyes, I find that kind of racist, but we'll just fix on that one. But definitely for American animation, it's everything about head shape and like eye development. I feel like that's one thing that traditional like cartoons that we're used to from the West, and also the type of animation that is done. I noticed that anime, they all tend to follow the same drawing rubric versus American animation can be like the claymation. You can have similar, like maybe you may have like automated cartoon drawing. I forgot the technical term for it that they use in anime. And that could be in American animation. There's a whole, you have like the doll setup, like you can have also kind of like kids shows, and they reiterate that into a kids show. So yes, skipping off that. So one thing I want to note is just the issue with American cartoons as of this point, over the past, like, let's say like 50, 60 years, both American and Japanese animation has taken from one another. I think right now, definitely America has always had a diverse set of animation tactics that they use to market. So you can see on the left kind of like American tropes of like head shape and really random features that make American cartoons. So you have Hey Arnold, and we all know the classic football head. It's ridiculous, but hey, we're gonna go with it, and the, like kind of crazy hairstyles and stuff that they go along with that. But then you also have within American animation, which makes it hard, and we'll see towards the end with the analysis, that America has also taken a lot of Japanese animation styles. We see that primarily with like the Boondocks, which was actually like what a newspaper like comic, and Avatar: Last Airbender, but they still hold on to like, I guess, an American view on how they were drawn. That will also kind of be a cool thing to see in the future. It's like maybe do like a video analysis and how the frame by frame it's changed, and the differences between anime and American cartoons. I think that's probably a better way of doing it, but once again, we're just gonna focus on the animation style. What is anime? Basically, everything on the left. You have American comics, you have American like faux anime that like tried to imitate it, and then you have digitally created content, which is on the top. Just a funny thing I always like to point out is that on the bottom right, you have old men in cartoons and old men in anime. You can tell the difference, and old women in American cartoons and old women in anime, just to keep it kind of comical. But yeah, moving on. Okay, so I did a neural network analysis, really basic. The base model was a dense neural network. Performed terribly, we'll see the results in the next slide. I then scaled up to a grid search on that baseline dense network, a convolutional network, and then two pre-trained models, VGG19 and an Inception ResNet version 2. Yes, here are the results. I did not want to blast you guys because I did that last time with all the graphs and everything, so I just decided to keep it simple. So basically here are the accuracy rates for each. To the highest was the CNN, I put CNN, and the Inception ResNet version 2. The reason why I ended up sticking with the Inception ResNet was because it did not perform, and this is the test accuracy, but it did not perform as well. I put in a random subset of like unseen pictures to test it, to just see how it works with I guess content that it hasn't seen before, and it did really. The CNN did not terrible, but it didn't keep that accuracy rate versus, like, I think I was getting like 70% for the 70% for the CNN, and then like the Inception, the Inception ResNet was getting about like 82. I tried to feed in data that was more or less hard for it to determine. And then, yes, so which model performed the best? I kind of already said Inception, ResNet version 2. Yes, and the reason being I already said that. Okay. The one thing that when I did another test showing Japanese style American cartoons. So that was what I kind of said before, is that you have like things like Boondocks and Avatar: Last Airbender that like kind of takes from Japanese animation. But then I also did it. I tried to pull American style created in like the content or marketed anime that was kind of mimicking American based content. There's actually a few shows, like I didn't know that Samurai Jack was actually Japanese produced. There's also Animatrix, which is the Matrix, but just in anime form, and he mimicked a lot of American, I guess, tropes and like digital animation. So I fed that in, and to kind of like throw the models off because they were predicting pretty well with like kind of stereotypical content. But with this, it was actually really hard. So basically, it predicted that everything was just basically an anime, which is, I think, in future reference is something I need to work on. And this may not be something that may be feasible with just a neural network on still images. I think another thing we would have to look at is definitely text mining of the content, of like maybe the scripts, or like still frame processing of like maybe small, like 5-second snippets of the animation, because I still believe that there may be differences in how, even though you may copy the art style, how the animation is carried out within the show may actually make more of a difference. So that's something that I would like to look at in the future. Yes, that is all. Next slide is just an example. This is the training set that I gave it. I gave it a mix of, on the left is everything that was Japanese related, but I guess the two in the middle are an American style type of animation. Everything on the right is American made, but imitating Japanese style. And my whole model performed terribly on these, so this is something I need to work on, but it did good in the classic anime and classic American animation, and deciding between the two, at least above 80%. So, okay, I'm done.
All right, thanks, Amir. All right, next up, Mo. Whenever you're ready.
All right. It says you cannot start screen share while the other participant. Oh, it's Amir, you have to.
Okay. I think I just toggled it, so you should be.
Oh, all right, I got it.
Awesome.
All right. So I did my project on recommendation system. So this is a recommendation system in a streaming world. Sort of overview of what I did. I created a recommendation system model that will help predict current and new user ratings. I pinpointed a specific feature that I found in the data set that can help generate recommendations for a new user, and also to understand the user's overall preferences based on the generated recommendations. The data source for my project was from the Movie Lens data set. I looked at the ratings, which had user ID, movie ID, rating, and timestamp. and also the movies data set, which had movie ID, title of the movie, and genre. And they each had over 100,000 rows of data. The data cleaning that I did, it wasn't a lot. There was no missing values. And I dropped the timestamp column because I didn't think it was relevant for the purpose of this project. I did a quick bar graph or histogram of the distribution of movie ratings. As you can see, most users rated the movies. It was on a scale of 0.5 to 5.0, and most users rated the movies 3.0 or 4.0. And then you had 3.5 and 5.0, but it was mainly 3.0 and 4.0 that they rated movies. The initial models that I used were K-nearest neighbors, basic, K-nearest neighbors with means, K-nearest neighbors with z-score, the single value decomposition, a variation of single value decomposition, and non-negative matrix factorization. My initial model results, as you can see, the models that had the lowest root mean square errors were the SVD model and the variation of the SVD model. They had 0.8725 and 0.8613, and the mean absolute errors were the lowest as well, 0.6706 and 0.6598. I did a grid search on each of these two models here, and my final model that I used was the single value decomposition model. And these were like an example of the results I got. So these are the actual ratings here, and these are the predicted ratings in this column. So if, as you can see, they predicted slightly higher for these first three, and then for the 5.0, it's slightly lower, but it was still a good prediction. It's not far off in terms of predicting the actual ratings. As you can see here, anything under the line here, which is mainly like 3, 4, 5 in the actual ratings, it's under predicted the actual ratings, and then anything over the line, it sort of over predicted the actual ratings, which is like 1, 2, and 3 as well. The residual error of predicting ratings, as you can see, it's between 1 and -1. So basically, when it was predicting the ratings, it would predict within 1, which is a good, model. It's not too much of an error when predicting the actual ratings, when predicting ratings. So I went into depth about looking at popularity bias. I found a nice paper that was done by Texas A&M University. So this is what popularity bias is: popular items that are overly exposed and recommendations at the expense of less popular items that users may find interesting. It hurts both users and items. So users are worse off because the system only learns the biased views of their true preferences. in popularity bias, popular does not necessarily equal better. The less popular items lose the deserved feedback, which are clicks, views, and also the economic gains that come from that. So there's factors that impact popularity bias. The four main factors are audience size imbalance, model bias, position bias, and closed feedback loop. Audience size imbalance, there's an inherent imbalance where there's going to be few items that have large audience sizes and a majority have a small audience size. The results of that are an imbalance in engagement data, which are clicks/views, even if the items are equally recommended. The model bias ranks the item with more clicks/views in the training data higher than the item with fewer clicks/views, even if the user equally likes both items. Position bias, there's the probability to examine items at top ranking positions is higher than at lower positions. So the matched popular item being recommended and ranked at a top position is more likely to receive clicks/views than a matched but unpopular item also being recommended but ranked in a lower position. And then the closed feedback loop is basically the popularity bias that's been generated in the past accumulates, which produces more bias in future models. So I mentioned all this because I created a predicted rating based on genre from the movie data set. And these are the predicted ratings for one specific user. Now you can see documentary had the highest rating for this particular user, followed by film noir, which is French for Hollywood crime dramas, and then followed by war. And I mentioned this because these aren't very popular. I don't think the audience I don't think these are the most popular genres out there. As you can see, comedy, action, adventure, drama, these are ranked lower. And so I think, using genre as a sort of basis for a recommendation system for predicting the ratings for a user could sort of help mitigate any popularity bias, maybe not eliminate it, but they'll mitigate it. So my final conclusions were that the single value decomposition model was the best performing recommendation system model. The predicted ratings error was between 1 and -1. And the predicted ratings for one user based on movie genre as I said, may help mitigate any popularity bias. The next steps, look beyond movies. Streaming has, I think, overtaken the traditional forms of consumption that we have for movies and for television as well. So I think, this data set really was mainly focused on movies. And so I think, future data sets, future studies should compare movie ratings with television ratings. And just to see, it's also a lot of the content that's produced now are in series forms. It's not one long movie. And so I think delving into a rating system that sort of focuses on or sort of pinpoints you know, movie format versus TV series formats could help have a better comparative analysis, create a better comparative analysis. Also include other features that may determine what impacts user ratings. So the actors that are in the movies, the actresses, the directors of the movies, you know, those other things could also impact the high or low ratings that users give. We should also look at the user behavior since the beginning of the pandemic, whether they favor other genres, whether, you know, what the pandemic has done to sort of change their consumption behavior in terms of content, and also explore popularity biases in the future models. And that's my project.
Great, thank you so much, Mo.
Thank you.
Last but not least, Sam. Let's round us out.
All right, do it. Can you guys see that?
Yep.
All right, hey, everybody. So I decided to do detecting pneumonia in chest x-rays for my phase 4 project. And I'm Sam, I know all of you. So some quick facts about pneumonia is that it's a form of acute respiratory infection that affects all lungs. And typically across the world versus what happens in the United States is a little different. So in most of the world, 14% of all deaths are for children under 5, killing about 740,000 children each year, or in 2019 at least, but it's pretty close to that number actually, if you look at the graphs. But in the US, actually, it mostly affects adults, and it's the most common cause of hospital admissions, other than women giving birth. And about 1 million adults every year go into a hospital and seek admission for pneumonia, and about 50,000 die from this disease. And so looking at these x-rays as an example, there's 3 different ways you can catch pneumonia, which is bacterial, viral, and fungal. Looking at the normal one all the way on the left, you can see that the lungs are clear. You don't see anything between the ribs. Bacterial pneumonia typically manifests in the upper right lung, as you can see where that 2 arrows are pointing, while viral kind of spreads, as you see like a little spider nest across both lungs. And in this case, obviously, for our presentation, we're not focused on this, but these are the 2 most common causes of pneumonia that you can find. So what happens when a radiologist decides to take an x-ray of your lungs? It's shocking to learn that there's an error rate of about 4%, and about 1 billion radiology exams are taken each year. So that means by this logic, about 40 million radiologist errors are taking place every year. And as an insurance company, my business case is to, for you to know and for me to know that every time you go to the doctor's office, if you are going through private insurance as well as public, they do request those medical records. You have signed off on that. And typically, if you don't sign off on that, they won't cover the cost. So it's kind of a catch-all approach there. So what if we would create a system to double check what the radiologist's evaluations are and what they submitted to your insurance company? This would increase patient safety and long-term care and reduce the chances of further complications, as well as save some money on both ends. So there's a business case for you. So source of data is the Women's and Children's Clinic, and I'm not going to try to pronounce it because I already messed it up. I practiced it, but I didn't do it right. There are 5,863 x-rays. They're all JPEGs. They're broken out to 2 categories. So a normal x-ray and pneumonia x-ray. We're not going to differentiate for this business case between viral and bacterial. They're selected from retrospective cohorts of pediatric patients from 1 to 5 years old. And all chest x-rays imaging was performed as part of the patient's routine care. And you can find the status set on Kaggle. So for my EDA, there's about a distribution of images was different for the train and test sets. So for the train set, we had about 5,216 images. For the test set, we had about 624. Both of the data sets were imbalanced and favored pneumonia in both cases. And we labeled all normal cases as 0 and all pneumonia cases as 1, regardless if it was bacterial or viral. We just labeled it as 1. And here at the bottom left, you can see the training data. When I mentioned earlier, about 5,216. Largely, it's close to about 30, a little bit over about 3,700, about 3,724 images of pneumonia versus the remaining, just like roughly around, I forgot, about 13 something. The exact numbers are on 1,300 somewhere. And then the test data set, which only had a total of 624 images, you can see pneumonia was around about 390 versus the normal x-rays were around a little bit over like 230s, in the 230 range. So imbalance favoring pneumonia, so we got to be careful there when we do start our process. For the models, I went through a 4-part iterative modeling process and started with like a baseline multi-level perceptron just to see where we were at by looking at the data. Got about a 75% accuracy there. And as I went through the process, I kind of really just focused on how can I improve this model without making significant changes to the data I've imported. So I didn't really change image size or rescale them in any way. I was really looking at improving the model, not really improving the images, because across the world, there's different levels of X-ray machines and qualities that are going to be different. So we can't really make a standard approach because not everyone will have the same fair access. So going from that baseline to a baseline convolutional neural network, I was able to get a 78% accuracy. I wasn't able to get the tune CNN in time for this presentation, but I will update that and let you know. But with my transfer labeling, I was able to project 90% accuracy with the X-rays, pneumonia versus not. The transfer learning so far was the best model. And this process is like generally referred to as a model that's trained on one problem. So one set of images and used on a second set, like our X-rays. I used what's called the VG16, and it's a data set of 14 million images belonging to 1,000 classes. One or more of these layers basically are trained on that model. And then what we do is we take what it's learned, the feature selection, which is what it's known for, and use that on our X-rays on top of what we added to the model. And we ended up getting roughly a pretty good distribution. Obviously, if we got to 90% accuracy, roughly we got to about 1.87% of the 624 images were predicted as normal when they actually had pneumonia, which is still less than the 4% if we're looking at a worldwide about radiologists incorrectly, diagnose, miss, if you want to look at that way. And about 7.94% of the 624 images were predicted as pneumonia when they weren't. But the model is pretty overall accurate at detecting normal cases and pneumonia cases. And I'll show you here on the next image. So here's a confusion matrix. And if it's a little confusing to read, I kind of put a little chart here in the bottom left-hand corner. So when we run our model, this is how we predict 0 is normal, 1 is pneumonia. And obviously, we're really concerned about the people who actually have pneumonia and they get diagnosed as having pneumonia, which the majority do. But the biggest concern is for the people that, they don't have pneumonia, but they do. I apologize. The biggest concern is for those people that are diagnosed as having pneumonia and saying they're fine. So that's where that about 2% error comes in. About 51 of the images were diagnosed as having normal and when they had pneumonia, but 2% overall is still a lot lower than 4%, and it could save us quite a bit of money over the long term here in the United States, and for our insurance company as well as our clients' time, and obviously life is more important. So in conclusion, insurance companies could use a tool to drive down the risks of false negatives, and then by checking the images after receiving a radiologist diagnosis and the X-rays, insurance companies could reach out for clarification when they don't come to the same conclusion. Obviously, insurance people aren't doctors, but just asking them to look at it again to confirm that that's what they came across would obviously be like a double check of the system, as well as comforting to know that your dollars are being used to actually, make sure you're healthy and you can go home and you don't have any concerns, or you don't go on WebMD that night. Our next steps, we could have doctors and technicians kind of crop out the areas they identify as pneumonia in the process, or they could remove the diaphragm and x-rays as a standard practice to kind of make it easier to see what's going on. Standardizing pixels, resolution, and sizes of the x-ray images would probably be a little bit more possible here in the US, not globally, but that is an option. And then we could widen the range, I'm going to say widen the range of the age, because mostly we're looking at children from 1 to 5 in this city in China, and the geographic distribution as well of the x-ray images. And then with more time, obviously I could research more effective tuning methods to try to get a higher accuracy rate. But that is it. Thank you.
Awesome. Thanks, Sam. Let me stop this recording.